So I hope to entertain you a little bit with this radio analog signal processing, or RASP. It's an alternative way at looking at radio, and we think that it has a potential to be really useful. Now, 45 minutes is very short. My group has been working in this area for the past few years, so my presentation is necessarily going to be a bit conceptual and superficial. I'll just skim through the surface, but I hope to give you a good idea. So that would be the overview. First, I will introduce the topic and motivate it, and also tell you the fundamental aspects behind RASP, which is essentially dispersion engineering. And then we'll look at phasers. Phasers, they are dispersive structures that allow one to control signals in real time, and they are the engine of RASP. I will tell you what this is and how it works. Then I will tell you very briefly how to synthesize those phasers and try to keep more time for the applications. We'll go through a number of applications and see how this is working. This is a paper that is a review of some of these researches on RASP, if you're interested. So let me start. And as I mentioned, RASP, radio analog signal processing, is based on dispersion engineering. And there are different types of dispersion, so I just want to recall this. The first one actually is spatial dispersion. This is what we have in apertures, antennas, photonic crystals, and so on and so forth. And what happens is that the spatial frequencies K are being scattered in different directions in the medium or in the system. So here, spatial dispersion engineering consists in manipulating the Ks. That's what people are doing on a regular basis. Now we have temporal dispersion. The temporal frequency is manipulated in this case. So we have a dispersive medium where different temporal frequencies are delayed by different amounts. That's what we have in glass at optical frequencies, Fourier transformers and things like this. And this is what we are using most of the time. It's not very common at microwaves, but we do this here in a systematic fashion. And we can have the combination of the two things, like in the case of gratings, where temporal frequencies are being decomposed in different spatial frequencies, different directions, like in the prism, and occasionally we'll use that as well. But we use mostly the temporal dispersion. Now, if you have a medium, it has to be causal. It means the response has to come after the excitation. And this imposes some constraints on the frequency response of the susceptibility of the medium to be causal, okay? But if you are causal, there is still a lot of things that can be done and that have been very little exploited, at least in the microwave regime, I think. So this is illustrated here. This is a dispersion diagram. And the idea is to manipulate this phase shape in various fashions to obtain lots of effect, lots of applications. It can be guided, radiated, multiband, non-reciprocal, forward, backward, and so on and so forth. So we want to systematically exploit this manipulation of the phase for novel types of devices and systems. Motivation, why would we do that? Well, this is not very original to say that we need faster, more reliable, ubiquitous systems in communication, instrumentation, radar, and sensing. That's the kind of boring, typical introduction you have in many papers. Now, in particular, what has been done over the past few years is to put lots of emphasis on the digital signal processing for obvious benefits that have been leveraged. But if you want to go to higher throughputs, then you have some bottlenecks. You have the cost of the analog digital converters. They are also consuming huge amount of power, so drain the battery very quickly. There is the complexity, and there is the limitation to higher frequencies, forthcoming terahertz technology, and so on and so forth. And an example is 60 GHz communications for all of these devices where we have lots of challenges. Now, this DSP is used in the lower end of the microspectrum. So we try to get inspiration from what people do at other parts of the spectrum, in particular in optics. In ultra-fast optics, people have to handle things in real time because they are just too fast. And so they have done this kind of optical signal processing that's done in real time. There is no buffering. The processors are electromagnetic processors. So we want to try to borrow some of these ideas so that in between, at microwave and millimeter wave frequencies, we can come up with a new technology that could potentially address the challenges of tomorrow, including 5G. In 5G, in principle, there is a there is a 2 orders to 3 orders of magnitude throughput increase that will be required. And so far, no one has an idea how this will be done. The current DSP technology cannot do that. So we speculate here that RASP might be a solution to address this challenge. So first, let me tell you what RASP is compared to conventional DSP technology. And for this, I just show you here two fundamental operations. Of course, there is the Fourier transform used in OFDM, for instance, that gives the spectrum of a time domain signal. And a bit more complex, there is the short-term Fourier transform, also very useful, that gives you the Fourier transform of a gated signal. So you have the evolution of the temporal frequencies in time in a spectrogram. Now, the way this is conventionally done as of today is to use DSP processors, discrete Fourier transform FFT, short-term FFT, and so on and so forth. And you have a few devices that do that. But they require this heavy processing, and they require the buffering of the data. And so the speed is low. And as I mentioned, the converters that are being used have limitation in terms of frequency, how high you can go in frequency, and even more on how much the absolute bandwidth can be because of the consumption issue and so on and so forth. So we want to try something else. We want to try an alternative here. And instead of doing the processing in a baseband, we'll do it in the RF. And how are we going to do that? Well, the point is that everything is going to be performed with analog systems, and this is going to be performed in real time. So you see that we'll have some electromagnetic structures that we call phasors. They can be guided wave structures, they can be radiated wave structures, and so on. And we'll present this in some details, but essentially that is the point, and we expect here low cost, fast processing, and scalability. So analog signal processing essentially consists in processing signals in real time using group delay engineered electromagnetic structures. Now, the group delay, of course, is the derivative of the phase. So what is commonly done is to expand the phase of our Taylor series, as you see here. But we need to keep at least the second order term about the center frequency, because this is the term that will give you a frequency depending group delay. And that's what is going to bring about the dispersion. So the simplest way to see that is the well-known effect of a chirping common in optics and in radar processing. If you have a modulated pulse that gets into the system, and if the system has a group delay that is a function of frequency, for instance linear, as in this case, what's going to happen, of course, is that the different frequencies propagate at different velocities, and so we have a spreading of the pulse. And at the same time, the frequencies are reorganized in real time. You see here that the low frequencies experience a small delay, so they arrive early in time. High frequencies, large delay, late in time. So that's chirping, and that's the basis. And usually in microwave engineering, this is a parasitic effect because it distorts the signals. But in RASP, this is the very basis of things. Now, this is an uncontrolled type of thing. What we want to do is much more sophisticated synthesis. And here is an example that illustrates the idea. Imagine that we have a two-tone signal at the input of the system, representing two channels, and we pass it through such a system. If we can get a group delay of this type, a staircase type of group delay, then what's going to happen is that we are still going to discriminate the two channels in time, because one experiences tau 1, the other one tau 2, so they're going to be separated. But then we have here plateaus. So it means each channel sees the same group delay, and we avoid dispersion and aliasing in time. So this is just an example. But if we want to generalize the concept, what we have to do is we have to be able to control the group delay versus frequency, and therefore the phase versus frequency in a quasi-arbitrary fashion. And the device that does it, we call that a phasor, because it's systematically controlling the phase. It phases signals as filters, filter them in terms of magnitude, if you wish. So let's say a few words about those phasors and what would be an ideal phasor. Nothing to do with Star Trek type of lethal weapon, of course. And this is something that has been used in acoustics and actually in electronic music in the 1960s. So essentially, it's a device that should provide a group delay that is fairly arbitrary within the pair span of interest. And ideally, the magnitude should be flat. I'll show you why this is important later. Okay, so that's an ideal phasor. Now, there might be different approaches to do that. At least there is two roads. One is what I call the material road. And for this, we can use natural materials like ferrites. You know, they are heavily dispersive, need a ferromagnetic resonance. We could use metamaterials with engineered dispersion, or nanostructured material that themselves have very interesting dispersive responses. This road, I think, is best for radiative devices, antennas, and scatterers. The other road borrows from the body of literature in filter theory, and that's the network road. In this case, we are not interested in material properties like here. We're interested as how the phase is transformed from the input from port 1 to port 2. So it's a point-to-point thing. And so here we can use some of the works that were done before, but this time to engineer a frequency-dependent group delay, and that was done for equalizers and cross-coupled filters. I'll say a word about this later. And this is working best for guided wave devices and components. Now, actually, the way we historically started the thing is we were interested in metamaterials and some kind of those meta transmission lines. You see some of the composite left-handed transmission lines here. And the idea was that you had an electrically small unit cell from which you had electric and magnetic moments, magnetizations and polarizations, and effective parameters, where the unit cell is much smaller than the wavelengths of the fundamental harmonics that is the strongest excited in the system. And so what you could have here is simply at low frequencies you would have a backward negative index wave, at high frequencies forward. You could have here two eigenstates that could be matched, and if this is the case, you have a smooth transition between the two. So here is, in that case, a very simple representation of the phase constant and therefore on the phase. Of course, this phase is heavily nonlinear because of the hyperbolic term that you have at low frequencies here. So that could be designed, but still, this is a rigid form. There is only a limited number of degrees of freedom in it, and so that's fine for some radiative applications, but we want to do something much more efficient. So here is what we do with dispersive network phasers. We're interested in the wave phasing from the input to the output. Here we have a C-section system. A C-section is a couple line coupler that is N-connected. And when this is a quarter wavelength, then the wave is trapped into the system, it resonates, and there is a kick of the group delay at that frequency. Okay? And the tighter the coupling, the more the kick. If the coupling is 0, you just have a transmission line, and the group delay is flat. So now, the simple thing that you can do if you want to get a linear group delay, which is a quadratic phase, for instance, that's a very useful one, is you just need to cascade a number of those C-sections with different sizes, each of them having a kick at different frequency, and then you can sort of mold the type of group delay response that you want to have. This is a transmission type of device. Here there is a reflection with discontinuities in a waveguide. For instance, you can reflect different frequencies at different locations. That's the same principle as for gratings. And you can apply more sophisticated concepts that were used in the filters. You can apply cross-coupled systems. We have a lot of resonators. They are interconnected in complex fashions. And what you do here, if you look at the transmission function, instead of placing the transmission poles on the imaginary axis that will give you zero magnitude transmission, you place them outside in the complex plane, and this is manipulating the phase in a way to obtain some kind of bandpass, all-pass filter, but with a phase that can be fully controlled. So I'm not going too much into the details of the synthesis, but it turns out that it is possible now to control the dispersive phase, tau of omega, in an unprecedented fashion, and following a number of works that were done in previous years. Let me show you some of those conventional microwave phasers. Those in microwave photonics, they are gratings that's reflected, chirp lines by the group of Professor Sorolla, Falcone also here, and all-pass filters. The reflection type, they have just one port. So it's necessary to use a circulator that converts this one-port reflective system into a two-port system with controlled phase. We can also use directional couplers to combine them. And the other two ports that are inherently simple because we transform the phase from the input to the output. In the past, people used magnetostatic wave systems. They are very lossy and require a magnet. Or there is the surface acoustic wave devices. They are limited in frequency, not appropriate for millimeter wave and terahertz. And so we prefer passive structures, regular waveguides, meta lines, C-sections, combinations of them, and some other structures. Remember, we try always to have a large group delay swing to discriminate the frequencies and to have a high resolution in the system. More recently, here is a list, a gallery picture of some that we worked on, stripline structures. They are folded C-sections having some fractal features in them. That's a CRLH system with enhanced coupling for enhanced resolution, hybrid structures, waveguides, and they can usually fit in a chip. To illustrate the type of problems and things that we have to face with, I'm just going to present one of them. And this is this C-section that you see here is non-uniform. So what is the usefulness of this type of thing? If you look at the system I showed before with uniform C-sections that are cascaded like this, a fundamental problem that you have is harmonics. Of course, this is a distributive structure, so if you have a peak of group delay at omega 1, you'll have the next peak at 3 omega 1. And that will prevent you, for instance, to get a negative chirp, a negative group delay through this point, because that's going to bring it up again. So there is a fundamental limitation of harmonics in those distributed structures that we want to solve with non-uniform C-sections. Also, if we want the structure to be quite small, we'll just put a small number of units here, but then we'll poorly sample the desired straight group delay, and we'll have these ripples. If we want to avoid those ripples here, we put more elements and we have a better sampling. But of course, the problem is now the structure is longer, the unfolded length is more, and so the average group delay is much higher, and inevitably you'll have much more loss. Now, if you use this uniform structure that can be seen as a limiting case of the uniform one with infinitesimally small sections, then you don't have any more harmonics, making these non-uniform breaks those harmonic peaks, so you can extend the bandwidths, and you have maximal degrees of freedom to fit any type of group delay response that you wish. And you will see some quite impressive ones in a second. So we suppress the harmonics. As I mentioned before, for the same amount of group delay swing, so the same amount of resolution in the processing, we get much lower loss. This is the S21 that we get for this structure compared to that one. And actually, you see here the type of group delays that we can obtain. Very unusual. In the filter world, the group delay, people always try to make it flat, and there is a little bit of kick at the end of the stop bands. So here what we have is Chebyshev group delays. You see here the first order, the second order, third order, and we can do many orders in this fashion with this type of structures. You see here an example of a device. You see the non-uniform coupling, the C-section in the end, and so on. And I will show you in the applications what this can be used for in a multiple access system a bit later. Now, I said there are two routes to do phasers. There is the material and there is the network. Here is a hybrid route. You see this type of coupled C-section phaser, and that's the group delay that can be calculated analytically from the coupling of the coupler and theta, which is the electrical size of the structure. If you use a metamaterial of this type, the metamaterial itself has constitutive parameters that can be strongly dispersive. This is here a ferromagnetic nanowire material. It has ferromagnetic resonances, actually can support 2 of them. And in this area, you see that you have an inherent strong dispersion from the material. So what happens if you put this on that? Well, the thing is that this electrical size, electrical length now will see the dispersive permittivity of the material. And if you co-design the material and the C-section structure together, what you can do is you can dramatically boost the group delay swing here. This is done in this area. You could boost it much more in that area. So that's a co-design, and you could get huge resolutions in this fashion. Thing that we got recently interested in is non-reciprocal phasers. So they are essentially phasers that have a group delay when the wave propagates in one direction, and another group delay when it propagates in the opposite direction. That can be used for very interesting, for instance, base station relays that will listen in one direction and talk in another direction. And actually, we did this in a cross-coupled configuration, and that requires non-reciprocal systems, typically gyrators. And very interestingly, people got interested in non-reciprocal systems that don't require a magnet. Here we had a paper some time ago where we used a metamaterial that was mimicking ferromagnetic materials. You see we have electron spin precession and rotation of currents only along one direction. So if you use a transistor to load the rings here, the currents flow also along one direction only, and you can have all the effects that you have in magnetism, but without magnet, just using transistors. And so those type of systems can be incorporated in non-reciprocal phasors to have fully integrated phasors and related applications. Oh, just a word about the loss. Of course, the loss in regular materials always are proportional to the frequency. The higher the frequency, the more dielectric and the more conductive loss that you have. Now in phasors, the interesting aspect is that the time the energy spends in the system is stored in the system depends on the frequency. And the higher the time, the higher the loss. So I don't want to get into the details, but just want to tell you that there is a balance. And if you have a structure with an up chirp and a down chirp, typically the magnitude tends to be unbalanced. Okay? Now that is an issue. That is an issue. I'll just show you intuitively why this is an issue. Here you have an input signal, that's a rect as you can see, and that's the output signal typically of a phasor. And as I will show a bit later, what we have at the output is the Fourier transform. So you see the envelope here is a sink, which is the Fourier transform of this signal. And this is going to be a time domain that will be mapping to the frequency. The problem, if we have this magnitude unbalance towards high frequencies, what's going to happen is that the spectrum is going to be completely distorted. So, and here this is very strongly exaggerated. But if you have magnitude imbalance, all the processing that you do in all the applications will experience this type of undesirable effects. So that's something very important to keep in mind. And there are different ways to combat this. One of them is to use the standard resistive networks. But a smarter one, perhaps, would be to use directly in the synthesis that I'm going to talk about. Knowing that the loss tends to increase with increasing frequency, you distort the synthesis, and then you end up with a magnitude that's flat. It doesn't matter so much if the magnitude is incurring some loss, because remember that you have a full processor in an electromagnetic structure, so you have to compare this with a full DSP system with ADC loss and so on and so forth. But it does matter that the magnitude remains very flat. So that's a problem that can be addressed. Now, I'll give you just a few descriptions of synthesis. That's a little bit tedious, so I don't want to get into details. The goal is just to present a bit of flavor of that. I'm not going to talk about the material dispersion engineering, that's going too far, but more the network one. And here we borrow from filter synthesis. Going back in history, 1 century, people did periodic structures in the beginning. We have, of course, stop bands, but it's very hard to control the design and also the phase. You know, it comes as it comes. And then there was the image parameter method. In this case, at least you can place a cutoff frequency depending on the parameters that you have. And also you can put a transmission pole. That's one step beyond. And then the insertion loss method, where you can fit specified mathematical responses. And this can also be used here to some extent. But so far in the literature, what people have done in filters essentially is equalization. People are systematically looking for a flat group delay. And so what they have done essentially is equalizers. Starting a long time ago, first with lumped lattice circuits like here. Steinert at Bell Labs actually was the one who introduced the C-sections and also D-sections. There are two successive couple line couplers with an N termination this way. Crystal came up with very nice equalizers in the form of those couple line structures with an end termination. And as in optics for gratings, he used here a circulator so that the system became a two-port system. David Rhodes, of course, interested in synthesis, did synthesis for coupled waveguides long time ago. Later, it was extended to more general coupled resonator structures. And here Hank came up with a very useful algorithm for R-ASP. And this algorithm allows one to generate a polynomial that has a phase that corresponds to the phase that you want. So that's one of the key aspects. So we can use some of this body of knowledge and literature that is, for instance, summarized in this book for our interest. So let me show you just one example. Here you see a number of C-sections, a number of phasors. They are typically simple phasors here because you see the C-sections, they are alternated, so they don't couple to each other. And here this is a serial diaphragm waveguide structure. This one is more complicated because there are strong coupling between different C-sections. So let's look at this type and see how the synthesis can be made. And if you have a given application, then you have a specification in terms of the group delay. Okay. Now the transfer function is in terms of the phase, so you just integrate that and you get the phase. And then you go from the bandpass to the low-pass domain, because that's where you have the prototypes. And what you do is that you simply discretize the frequency function. So you discretize the frequency, you discretize the phase, and you have n elements, 2 vectors. And then you can apply this algorithm of Hank that eventually gives you a polynomial whose phase is the phase that you desire here and that phase there. So that's kind of the key. And if you have here an all-pass system that is a reflection type 1 for simplicity, then the transfer function is just essentially having the phase to a factor 2, the phase of this polynomial. So you have the input impedance, you can use a long division, and then you can calculate all the low-pass prototype elements for that system, and then you use the conventional filter techniques to get your structure. So it very much looks like a filter, except for this small detail, but in the end you have a group delay synthesis of the system. There are a lot of structures that were done. Many times the group delay is a linear function of frequency. Remember, that means a quadratic phase, and that's what is used in real-time Fourier transformation that I will show. And there are some more complex phasors that can be more compact, where you see here tight coupling between different C-sections, so that provides more resolution. Here you have an LTCC implementation, you have vertical and also horizontal coupling, and here you have a CRLH type of structure that enhances the coupling and therefore the resolution. And for those cases, optimization is required. I will show you one type of optimization that could be of interest. But now let me show you a bandpass technique of the synthesis here. And as I said, we want to control the group delay, but also we need to take care of the magnitude. So how do we do that? Here we decide to have the transfer function that has the phase that is entirely due to the denominator, the Hurwitz polynomial in the denominator. And the magnitude here is going to be a real polynomial. So the magnitude and the phase response, magnitude and phase, are going to be completely independent from each other. I don't go into any of the details. It's the only thing I want to tell you. So by generating the proper denominator polynomial, you have the phase, and then you can do any type of magnitude engineering for P. And then what you do is you sacrifice essentially F, which means you put the garbage outside of the passband so that you have maximum flexibility for phasing in the passband. Okay? So you see here a linear group delay, and you see here that the magnetic response is of Chebyshev nature. And if you have more complex things, of course, you need to do some optimization. And here's a case where we did a space mapping optimization type of thing developed by John Bandler. And typically, it starts with a crude model, a coarse model. And once you have a very good initial coarse model, then the fine model can be reached very, very, very quickly. So you can have very quick convergence. So you see a beautiful coarse model here is to use the system where the C-sections are not coupled. They are separate from each other. And we have analytical solutions for these things. And so this is used as the coarse model, and then we run a number of iterations in this technique. And if we have a specification this way, initially we are a bit off, but very, very quickly already at the second iteration, we get a very, very, very good agreement and eventually a very small error. And so a very efficient design can be done. Now, I mentioned you this non-uniform C-section structure, just tell you how to design, how to synthesize that. Very simple. We have a specified group delay. And then here we have a coupling that depends on the position Z. So what can be done is simply to expand the non-uniform coupling in terms of a Fourier series. We initially select a set of coefficients here. We pass these through the system. We calculate the local impedances from the end all the way to the input, which gives us the scattering parameters and hence the group delay. And if we are not happy, we use optimization, we change those parameters until we get the proper group delay. And this is how we obtain actually these Chebyshev group delays that I will be showing later. And so that's giving you this function C of Z, which is the coupling along the structure. You see, for instance, for the first order Chebyshev, there is a very little coupling at the input, and then there is higher coupling. So reading this, you can see what type of layout you would obtain. Okay, and actually you can explain very nicely the correlation between the group delay and the electromagnetic field distribution along the structure, which is done in that paper. Okay, let me go through some applications from a very conceptual point of view. And the first one is a fundamental one that is used in optics. It's real-time Fourier transformation. So I just want to spend some time because it's so important. You see here, there is a time domain signal. And what we want in the end of the day is to have the spectrum in a real simple fashion with a phasor, essentially an electromagnetic structure. And that will be in real time, as I showed before. Okay? So see how it works. What we do is we take this signal and we multiply it, we mix it with a ramp. So here you have a frequency that is going down with time. It has an impulse response of this type. And at the output, we just have the product of these two things, and that's how it looks like. And now we have our phasor, okay? And here we engineer the phasor to have a linear group delay, so quadratic phase that has the opposite shape. And so what happens, of course, at the output, this is a linear system. You have a convolution of the input and the impulse response, that is the opposite to this one. And interestingly, you see that the tau square here is going to cancel out this one. The t will go out of the integral. And what is left under the integral for the output signal looks like a Fourier transform. It's a Fourier transform, but it's a Fourier transform in a time domain. If you call this omega, omega of t, you have here the temporal frequency. Okay? And sigma that is there is nothing but the slope of the phasor. So look at what you obtain in the end of the day. You obtain here in time on an oscilloscope, or in a portable device. You obtain here the Fourier response of the system, but in a time domain. But since you know time, you can map the time onto the frequency, and then you get the spectrum of the system, and that costs essentially nothing. And this can be done in real time. Very importantly, sigma, the slope of the phasor, is the resolution. You see, if sigma is very large, then the step in the frequency is very small. So we have a very high resolution in the Fourier analysis, and that's a key parameter. So you need a lot of dispersion to do that, and tricks like hybrid material network synthesis can help. So we'll show you some examples. Essentially, this is the key point. Just to mention that the system could be even simpler. You could even get rid of this ramp product here. You could have only this if you have sufficient amount of dispersion. So you see an electromagnetic structure is in a sense a full processor, and Fourier transform is what is used for OFDM, so we could have a real-time OFDM system perhaps. So let me show you a first very simple application. I already mentioned we want here a frequency meter. Very simple. We have a phasor, we read the group delay, and knowing the group delay, we know the frequency. Now, many times we want to crank up the frequency resolution. So here is a very nice trick. It's a loop, it's a feedback trip. The wave goes through, it gets dispersed, and then we re-inject it a number of times. Each time the wave goes through the phasor, the slope is doubled. So eventually, with a simple phasor, you can have a very, very high resolution. See, if the wave has gone only once through, imagine you have a two-tone here, things are being mixed up. The second pass, they start to separate, but not enough. And then you go a few more times, and then the separation is complete. So that's actually a simple way to do a very high resolution frequency meter. You see here for different number of turns in the loop, you get a higher slope. It means a higher sensitivity in the frequency discrimination. This looks very, very complicated, but what it is simply the following thing. It takes a pulse at the input, and it delays this pulse by a given amount that can be controlled. That can be controlled actually with a local oscillator. So this is a tunable pulse delay system that has a number of applications. Just in a nutshell, you see, you come up with a modulated pulse here, you pass it through a phasor, so you have spreading and chirping, and then you mix this and you take the lower sideband. So there is a negative sign in the mixing, and so the time is reversed, it's being flipped in this fashion. And then you pass this exactly through the same phasor as there, that has the opposite form, so the total group delay is flat, and then you retrieve exactly the same shape as the input. So there is no aliasing also in this case. You see the experimental result, you get very clean pulses, and I will show you now a simple application of that. This is pulse position modulation for impulse radio. So the system is simple. You have a clock that is driving the bit stream, and that's also driving a pulse generator. So if you get a 1 in your message here, then you excite here a large group delay through the VCO that is going to multiply that signal. Large group delay, the carrier has a large group delay. It means you will have a pulse that is placed later in time in the slot. If you have a 0, the 0 is multiplying the pulse here by a carrier that has a smaller delay, so you get closer. So you pulse position modulate the signal, and if you have that was a very early work, but if you have a very good phasor design, you can do quaternary and so on and so forth. You can do very sophisticated type of things. And that's scalable to any frequency you wish. That's non-coherent. There is no clock recovery, and it's fairly simple. 4 minutes, okay, so I think I'll skip. You can do other things. You can do RFIDs, spectrum sniffers. It means you here you detect the channels that are in the environment, and in the time domain, when you have a zone, a silent zone, it means that you have a channel that is available for transmitting. So that's useful for cognitive radio and so on and so forth. Here is an example where we use not only temporal dispersion, but also spatial dispersion. So that's a real-time spectrum analyzer. You see here you have a chirp signal. If you look at it in the time domain, you see that the instantaneous frequency is increasing, but that's pretty much it. If you look at the spectrogram, so the time and frequency information, you see that this is a quadratic chirp. So for all time variant signals you find in biology and UWB and so on, that's useful to get the spectrogram. So the way we do it here is with a leaky wave antenna. The test signal is passed in the leaky wave antenna, and there is a mapping from temporal frequencies into angles, which means spatial frequencies. So that works like a grating. So you see that there's a signal that we want to get the spectrogram of, and the different frequencies radiate in different directions. Their time evolution is monitored through envelope detectors, and in the end we get the spectrum. Now, compared to the state of the art, essentially this is just an add-on for commercial sales, but that cannot take any reasonable bandwidths. So here you can in principle do any bandwidths that you want, because it's a real-time system. You can also come up with very fast systems like routers by controlling the analog pattern of that structure through varactors. You scan the entire space and you pick the best channel at all times. So you steer away from destructive interference, and actually that led to a company. if I have one more minute now going into radiation, I have just 2 more slides. You know, people have done lots of multiplexing. There is time, frequency, division multiplexing. There is CDMA. You can multiplex on polarization, on MIMO, and now on DCMA that I presented in the previous slide. But there is a recent interest for what is called orbital angular momentum multiplexing. I think it's extremely interesting. And in nature, you have plenty of things that have orbital angular momentum in the sense of they are vortex, like the DNA, that there is a twist in the shape of things. And in electromagnetics, what this means is that in contrast to a plane wave where the phase fronts are planes, by definition in a direction perpendicular to propagation, now the phase fronts are going here to be spirals. And that's very much the same thing as what you have in a circular waveguide. This is this azimuthal type of dependence of the field, but now this is in free space. So you can radiate this. And since this is building an orthonormal basis, you have an infinite number of possible ways of orthogonally coding signals and multiplex the signals. There are plenty of applications in the nano world, in the macroscopic world. So here I'll show you a funny one that we do for multiplexing. Unfortunately, the simulation, the animation doesn't work. But what it was, it's a straight liquid wave antenna. It radiates, and so the phase fronts, of course, are planes. So you have a plane wave. And now progressively you bend this antenna into a circular loop. So the phase front, they start to bend and they collapse into a spiral. And here you get a beautiful orbital angular momentum wave from that spiral. And that's the way the spiral looks. That's the antenna from the top. And here at the bottom, we have a feeding network. So ultimately what it does is the following. You have here 2 inputs. If you come up with that input, you have a data stream here. Then you generate a rotation in this direction. You radiate with the orbital angular momentum that is right-handed. And if you excite the other input, you rotate in the opposite direction, you have the left-handed orbital angular momentum. And so at the same frequency, at the same time, the same polarization, you really have multiple access multiplexing in the orbital angular momentum, which I think is very interesting and promising for the future. My last slide here is to bring the phasor concept into antennas and to have a real electromagnetic radiative processor. So the idea is very simple, like in field antennas, you could radiate out the signal that has been processed by a phasor, by a sequential treatment, but you could also combine the 2 in one device. And then, of course, that will be smaller, lower loss. You see here an example. We take a log periodic dipole antenna and we modify it. We design the teeth of this antenna such that we go from the typical hyperbolic dispersive response, for instance, to a linear one. And I show you that linear one produces a real-time Fourier spectrum. So this antenna is a real-time Fourier spectrum analyzer, and that can become a very interesting communication system that can also be used for DCMA. So each access point in the system will have an antenna that will have different patterns that will include the discrimination of the channels directly onto the electromagnetic device without any processing for any frequency from DC to daylight. So conclusions. I presented radio analog signal processing, and I speculated that this could be a technology for tomorrow's radio. It's very different from what is being used. For those who just arrived, the idea is very simple. You need to get a group delay that is a functional frequency as controllable as possible to separate things out in real time. And then you have seen a number of phasors, some of them borrowed from the body of literature available in filter synthesis, others use materials. The synthesis can be done in a very accurate fashion. I presented a number of real-time system, one of them being dispersion code multiple access that's currently being developed into an industrial product. And to conclude, I would just say that I feel that this field, inspired by ultrafast optics, is a very rich scientific technological area, and I hope that it will solve of today's problem in radio. Thank you very much.